Welcome. I'm Liz Taylor, ocean explorer, naturalist, and entrepreneur.
I'm Sylvia Earle. I'm an oceanographer, National Geographic Explorer, founder of Mission Blue, and I'm an ocean elder. Thank you, ocean elders, for sponsoring this program.
Absolutely. And this is our show, Dive In, where we host informal and open conversations with the ocean community on topics of wonder and interest. We're glad to be back and hope that everyone has made some time to be outdoors. You can ask questions in the Q&A box, and then later on, we'll get through as many as we can towards the end of the program. And we'll have some interesting links for you to refer to in the chat as we get along. And as we get underway today, we want to remind everyone that the world
is
blue.
Oh, come on.
Today, we are incredibly grateful to have Professor Ved Chirayath joining us. In addition to being a longtime friend and colleague, Ved is Vetlesen Chair of Earth Sciences and another National Geographic Explorer, and the inaugural director of the Aircraft Center for Earth Studies at the University of Miami. Welcome, Ved.
Thank you. Thank you for having me.
You know, we met when you were just beginning to use drones and thinking about looking at space and looking at the ocean with space tools, and it's been quite an incredible journey.
Well, that's putting it mildly. You know, I think Sylvia pinched my arm one day in the Bay Area and turned me from an astrophysicist into really an oceanographer on the spot, and I've been hooked ever since, and really trying to use everything I learned in theoretical physics and astrophysics and space exploration, applying it to what I've come to realize is the coolest planet we've ever discovered or found, and it's right here, and most of it, of course, is unexplored and under a pesky layer of water. So it's been a fantastic journey, and I'm happy to share kind of development since that first meeting. But yeah, Sylvia's been a bit of a hero and inspiration to me, and watching you too has kind of given me a newfound lease on how to explore the universe with a conscience and to really understand life in its entirety in one of the most successful biospheres that we know of. And I spent a lot of my previous career looking for planets outside of our solar system and even within our solar system, looking for life within it. And we have not found yet one sample of any life, let alone a biosphere teeming with intelligent creatures that are related to us. So yeah, there's a lot to cover today, and
it really is. It's the whole other worlds programs and things they're fascinating. You know, when Sylvia and I came down to NASA Ames, and we were there for so many years working away there as well, and just there's so many correlations between the ocean planet and everything else.
This is part of the universe.
It is part of the universe, yes.
It just happens to be the closest planet of all.
Yeah.
Right. So I can share some slides, or
yeah, let's do it. You can share your screen.
All right, that'll be
awesome.
All right, how's that coming through?
Excellent. Yeah. Excellent. Right. Thank you.
So I'll just give you like sort of a brief overview of the latest of what I do, and then we can open up to discussions. I am an astrophysicist sort of in recovery, although at this point I think I've been in this field now almost 10 years, so I feel more a connection with the ocean. But the reason why I moved into oceanography so heavily, one was meeting, of course, Sylvia. But second was just realizing I had created the picture of the sun and the moon you see here using technologies that I've developed to look at objects in space at high resolution. And I've shown this slide since 2012. It's still true, right? We've mapped more of these three celestial bodies, Mars, the sun, and the moon, than we have of our own seafloor. In fact, we lose entire jet planes on Earth, and it takes 10 years to find them with hundreds of souls on board. But on Mars, we lose a rover the size of a golf cart, and within 10 days, we can image the crash site and see what's happened. So yep. What's startling to me is that, one, there was just this technical disparity between what we has accomplished as a species in space, where nobody lives except for a few astronauts on a space station, and on Earth, right, where you have a biosphere that is incredibly successful, but also quite precarious and has a habit of making species go extinct, particularly ones that don't pay attention to the right things at the right time. So a lot of my efforts have been trying to translate the best of space exploration and astronomy and physics to mapping what is the most interesting world in our solar system that we know of. I'm hoping we find more on some of these ocean worlds, but that's been a main driver of my research for the last decade. And I'm happy to share one of the main breakthroughs I developed at NASA, continue to work on for NASA now, is the development of a technology called fluid lensing that can look through ocean waves to now 25 meters depth at the centimeter scale. So I'll share a little bit on that. And I continue to develop new sensors, but every time we develop a new technology, we see the seafloor anew, it opens up like thousands of new questions. It's a bit like if you think about how Hubble Space Telescope and Webb Space Telescope changed our understanding of our place in the universe through new data, right? Asking questions that you never thought to ask before. That is now happening, I think. Well, it's been happening in oceanography for a while, but we're now being able to pull back at least the shallow parts and see what's under there. So I continue to develop primarily sensors for NASA and a few other large agencies and National Geographic now. I do a lot of work on aeronautics platforms, despite being an oceanographer. I spent a lot of time at sea, but aircraft and spacecraft are really the way to study something as big as the ocean biosphere, right? It's truly gargantuan compared to even land. And so it requires a space-based system to really observe at scale. I've also spent a lot of time leveraging the best of AI to study these systems, because even if you do map these areas, trying to interpret what those data mean can really require another 100 years. So we turn to AI to try to pull out meaningful information about things like coral reef health and other marine ecosystems around the world.
Yeah,
So,
the data sets are so big.
yeah. So I'll share, like, one of the technologies, fluid lensing and fluid cam, and what we've been able to see recently with this and why it's so important is that these ecosystems, particularly coral reefs, are changing at a pace and a scale that's kind of unfathomable compared to what we see on land. This is a reef just off the coast of where I am right now in Miami. Florida's got the world's third largest barrier reef, and last year it went through a marine heat wave, the equivalent of like a wildfire underwater. And all of these beautiful elkhorn coral and staghorn coral were bleaching and dying off as a result of that heat wave. No other technologies could really see this except for divers in the water and this technology, fluid lensing. But it kind of underscores the need to get these technologies deployed now at scale, as we are losing environments like this so fast that we don't even know what we've lost until it's gone, right? So we're in this world that is changing rapidly, and on land we can see some of that change from satellites and from aircraft, but in the ocean we're still quite blind as to large scale changes.
It's one thing for me to say that when I first explored the Florida Keys back in the 1950s, it was truly a different world from what is there now. But the change continues to happen. And what you're able to do is not just show the change, but to measure the change. Again, it's one thing for me to be a witness and describe it, but science really flourishes with measurable evidence, which is where what you are able to provide is just, it really changes everything. And coral reefs represent an obvious first place to start, but I love it that you're looking beyond that. It's all of the ocean, starting along this most important part of the planet. You've worked also in Samoa.
Yes, at this point, I've done about 70 global missions. So Madagascar, Puerto Rico, Samoa, Guam. I mean, it's really there's a lot of oceans about. And so I can share, one of the other advances behind this. So in general, like ocean remote sensing is difficult. The reason why we haven't mapped so much of the seafloor is the view from aircraft from space. When you look into the sea, of course, is dark, right? You have a lot of light that's absorbed. And then the second phenomena is this phenomena of waves that can bend light and cause refraction. So this phenomena I called fluid lensing, and actually spent a lot of my time developing a technology and simulating the phenomena on the NASA supercomputers to try to understand what are the main physics at play. And you see this at a swimming pool, right? When you get deeper in the water, you can see objects distorted by waves. One thing that interested me about this particular effect is if you slow this video down, you'll notice that when waves have the right shape, they can magnify an object. They can also demagnify the object. So that's a phenomena that fluid lensing as a technology exploits. It uses those waves as free magnifying glasses to see something on the seafloor at high magnification, even though the sensor may be quite low resolution. The second phenomenon it exploits are those bright bands of light you see on the seafloor, which come from waves focusing sunlight down. They're called caustics, and they can be 100 times the intensity of sunlight at the surface of the ocean. So fluid lensing uses those two phenomena, the magnification and caustics, to see really deep in the water and at high resolution. And it does so in a way that can outperform really any other sensor we have because it's using the ocean itself as a lens. So this grew into an instrument called NASA Fluid Cam. There's a number of them now around the world flying on drones and larger aircraft. We have a helicopter now that's integrated with the sensor. And what these drones are doing are flying around reefs on island scales, so entire island reefs, and taking in raw data that are used for fluid lensing. So this is what typical data look like from an aircraft. When you look down at the ocean, you get, in addition to absorption in the water and refraction, you get strong reflection. And fluid lensing is able to use those two wave effects to see through that and then map the seafloor terrain in 3D. So that was that first animation I was sharing. And this was based on a campaign in 2016 in American Samoa, and we got down to about 0.5 centimeter resolution, which our coral community says is important because that's the scale at which corals grow per year is roughly 1 centimeter per year. So if you're trying to monitor them through time and quantify them, you need to be able to measure at that accuracy. Just to give you a sense of scale, that is a sea cucumber up here. So that was the kind of the result in 2016. During the pandemic, I spent more time working on the math, and one of my colleagues had been pushing me for ages to look through breaking waves, which I said, this is impossible. There's a reason why no one can see through here, right? But it turns out that, you know, all it takes is a pandemic and me sitting at home and not doing field work to realize you can look through this. So in 2023, for the first time, I demonstrated successful imaging through breaking waves, and it's revealing all these new coral species that only exist in that surface zone that no one wants to go in because it's too rough. We're finding, you know, dead bodies and lost items and infrastructure and all these things that end up on that reef crest, right? So this was one really big advance for fluid lensing, and now this one also beat the depth record and resolution record. So this is a reef in Guam that we're classifying at the centimeter scale over the entire island, and we're looking at that reef through time. So if somebody drops a scuba tank on a reef, we can now know when it happened and what it looks like before and after. And the managers that are responsible for this reef can institute policies and ensure that they can protect what is their most valuable resource for a hurricane that recently hit them, a Category 5, and this reef helped protect most of Guam from that damage. And that's the main economy, right, is based upon this reef being healthy.
I think it's really important for you know, finding and locating and then coming up with removal plans for you know, marine debris or derelict fishing gear too, because that's so destructive when it gets wrapped up in a reef and it just saws it apart over time.
Yeah, and you know, the surf zone it's hard to see. I mean, some of it we didn't quite believe because it just, you know, you have to really go there to like see. There's this one very fluorescent coralline algae that only lived under the the breaking waves. But yeah, now it's kind of been revealed successfully. And then I'll jump a little bit to other applications of the technology that have advanced since the early days. And that's been, my whale colleagues have been super successful, just like Sylvia, in convincing me that we need to use this technology to understand where the whales are, particularly when they go in and out of San Francisco's harbor. They get hit by cargo vessels and they just don't see them, right? The whales don't hear them acoustically because of an effect with sound waves being refracted down from ships. So one question we have is, can fluid lensing be used to see the creatures at depth, helping give ships an early warning sign? But then the second idea was, can we use it to actually identify individuals? And I'll share some new data that hasn't yet been published, but is a preliminary look at what fluid lensing can do for these creatures. And we're finding that, in fact, you can, in fact, ID them without waiting for a tail fluke in many cases.
Yeah.
Which was...
We used to think only, well, we were relying on the whale tail prints, but just a human being, it's the whole human being.
Yeah, it's not just their rear end.
Right, right. So I don't yeah, I don't know how distinguishable my rear end would be, but the whales are, I mean, at least with humpbacks, this works very well because they have all this nice, crusty life wrinkles and things. We're trying it on minkies and blues, and that's what I'm out in California doing every summer. But I've been promised smoother conditions in Antarctica, which seems like a false promise to me. But I've seen pictures of these bays that are flat calm. So we're hoping to test this out there. And we have, this is a little suction cup tracker on this humpback that falls off after a day or two. But that's how we're planning to kind of test how well this method works at different depths and with different species, and then hopefully deploy it at scale so we can know where are the whales, globally, where do they hang out? And then can you tell that information to the cargo shippers, right? Because they don't want to hit things either. And hopefully they will then, slow down when they see.
Just the idea that you can identify whales as individuals instead of just thinking of them as pounds of meat and barrels of oil. And I think some of your work with parrotfishes, it's also really transformative, but getting to know individual parrotfish is another. I mean, all creatures, every single living thing is distinctive in terms of their DNA, but they also have visible differences if we can just get smart enough, tuned in enough to be able to recognize them. Or think about octopuses. They all kind of look like an octopus, right? I mean, I don't mean just the many species of octopuses, but you get 50 of the same individual kind of octopus. If you really look at them, there aren't any two alike. We just have to get better about seeing what should be obvious. I know Liz is distinctive. You're distinctive. But sometimes to an octopus, we're just humans, just the primate.
That's right.
Yeah, I mean, every time I get to interact more and more with them, I do see lots of personalities. There are whales that are tremendously cooperative, and then there are whales that are, vehemently not. So I'm hoping we move forward.
But it's just such important work, I think, to kind of find ways that we can help with this issue of collision in whales, because in speaking to a lot of the people that are out there trying to disentangle them, they've reported that, like, the blue whale in particular, like, its response, if it thinks, or if it finally hears a ship coming, is it just freezes in the water. It doesn't like try to go away. It's sort of like a giant rabbit. It's just like, I'm camouflaging myself in all this blue water around me, is their kind of their self-defense. And so then they just become, literally just a sitting duck there waiting to be hit. So there are ways to kind of send aircraft ahead the same way. I guess right now you mostly hear about people using them to spot tuna, for extractive purposes. But if there's ways to get out there and engage local community to watch for whales and kind of help forecast and spot where they are, so there could be a really significant drop in the collision for some of these species, like the northern right whales and so forth, there's just so few of them left that we've got to figure out how to not hit them.
Well, they were around millions of years before ships arrived in the ocean. So
Yeah.
it's up to
Yeah,
us
they're at like close to 50 million years now, which is like 10 times longer than any humans have done. And that's the other thing that interests me a lot about, and why I got into cetaceans of all things, is that we're spending a lot of time at NASA looking for life, right? Trying to find intelligent life. And here is one of our relatives, a species that we now know has culture, has unique names for one another, has songs that propagate through the sea. They have a lot of signs, some tool use, a lot of signs and cultural phenomena that we would associate with humans. And yet we don't know how to even communicate with them, despite having a shared ancestry, right? And so it makes me wonder, and the reason why I like studying them is I think if we can understand organisms that are one of the rulers of their domain, right? These are one of the most successful creatures, mammals certainly, that have been around in the sea, that have survived multiple extinction events. They can communicate over long distances like humans, but they don't use technology to do it. Can we learn from that? And when we go look for life elsewhere in the universe, use it as a template for this is how we might make first contact. This is how we might learn how different cultures and organisms have a society that's like ours or similar to ours, but different, right? So yeah, for me, that's very exciting. And then the second is just how lucky are we that we get to be alive at the same time as the
Yeah.
largest animal to ever live. If you look at like the blue whale, it's only the last 6 million years, and humans came around the same last 4 million years, and we seem to overlap in that time period. And it's like, how lucky could we be to have this giant organism? And then to even think that we might lose it on our watch seems
Yeah. Ghastly.
kind
it's
of, yeah. It's just, I mean, as a kid, the one thing we all wanted were dinosaurs everywhere. And it's like, well, you've got the largest heart that's ever been evolved on Earth. It's the largest, it looks like physics dictates that you can't get much bigger than a blue whale, at least in Earth's gravity.
Mhm.
And then there's this creature that's just not only reached that physical limit, but is like thriving doing so. Of course, the first blue whale I saw just pooped in the water and then dove and said, "See ya." And then the sea was orange and smelled like krill for like a good couple of hours. But
Oh, yeah. Right.
anyway.
and they're smart
Um,
enough not to destroy the environment that they live in.
True
yeah,
enough.
We learn something from them.
yeah. Because I often do wonder what do we do when we do find life elsewhere? Do we treat it the same way we have on Earth, or do we learn that there are other ways of doing this that will not result in the extinction or destruction? And it's happened. People have conserved and brought back many species from the brink. Whales are a good example of that, right? There was a lot of progress that was made, particularly with humpback populations, and now we're seeing it rebound. And so I'm hopeful that this trend can continue, but some whales may not be part of that, is the reality.
Yeah.
So,
Uh,
another thing I've been thinking about is, again, this goes back a lot to just Sylvia's kind of cajoling me into thinking about this issue, is even with technologies like fluid lensing and fluid cam, we can still only see the photic zone, right? We're still relying on sun to get that signal down, even if, if it looks like the theoretical limit for fluid lensing would be around 100 meters depth, which is it's a large chunk of ocean. If you walk out from shore to 100 meters deep, it's a lot of area. It's around the same size as the land area. But really, to get to the rest of the ocean, we have to, of course, see much deeper. The average depth is 4,000 meters. I don't need to tell all this. But the second thing that kind of bothers me is we've been looking at the ocean with eyes that evolved, like my friend here, this lemur, in 3 primary colors, right? And we've evolved this vision system to find ripe fruit on a tree, which is not what exists in the ocean. So all the colors of light that are useful in the ocean, that penetrate very far, are ones that humans don't really necessarily see in. So this guy, this lemur sees trichromatically. It has red, green, and blue as primary vision receptors. But a mantis shrimp looks at a giant clam like this and sees 11 fundamental colors and 4 polarization states. And that's, for physicists, very fun and exciting, but it means that we're sort of looking at the sea in the wrong color. So just like the James Webb Space Telescope went up and it was designed as an infrared telescope because it looks at the early universe, Hubble looked at the universe in visible light and some ultraviolet light. We need to start looking at the sea not as monkeys do, but as the organisms that live there do. And to do that, we have to shift our vision to higher frequencies. So bluer and bluer, more ultraviolet light. Then the ocean starts revealing a lot of interesting secrets. And that was sort of the premise of an instrument that I developed at NASA called MIDAR, which went on to win one of its Invention of the Years. This uses active laser light in colors that transmit very far in water to see ocean organisms at depth. So deeper than you could see with sunlight. And you can put this technology on underwater robots and submersibles to map the seafloor, finally, in colors like we see terrestrial landscapes, multispectral colors that allow us to learn what we're looking at rather than just get a shape like you get from acoustics, where you take a sonar picture and you get a bump, right? We want to know, what is that bump? What is it made of? And to do that, we use light. Light carries a lot of information with it. So MIDAR right now flies on drones and on some surface robots on the water, and it couples these laser sources with the fluid cam as the receiver. And what we're able to do is essentially fly around with a very bright controlled light source that's pulsed. So you don't normally see the colors, it just is a white flash. And we keep that intensity of light to actually lower than what you would get from the sun. So it's never exposing animals to anything that they're not used to. But because we're seeing in very narrow colors of light, we can start doing some interesting things. And one of them is if we look at corals, for example, the typical picture we see of this is a Porites coral in Guam, is in sort of the center column here. We see red, green, and blue. But in the ultraviolet, which is in the bottom right, we see that this coral has a disease on the top that's only visible in that pigment because corals have a ton of ultraviolet colors and pigments in them. They're, again, like they're photosynthetic animals, so it's kind of not surprising that they have a lot of sunscreen that they've evolved in their bodies. But when they get sick, you can see the effects of that most prominently in frequencies of light that are not visible to humans. So, this is kind of like if you look at a flower with ultraviolet vision, you see a landing pad because bees see in ultraviolet, and flowers have evolved to primarily work with bees because they pollinate them. They don't really care so much about humans in terms of what they look like. So the same is true for what we're increasingly finding are these complex underwater worlds, is that the creatures that live there, don't really see in red, right? Red in the ocean is essentially black. And they primarily communicate using bioluminescence and have colors in the blue, in the ultraviolet, in the wavelengths that transmit very far. So evolution has figured out the optical properties of water and then has exploited that to preferentially have colors in those pigments. So I think it makes sense to start looking at the ocean in these wavelengths. And so I do a lot of my new work is at nighttime, surveying reefs using ultraviolet sources of light. The other advantage of using wavelengths like that is you can see marine plastics that have been biofouled and are new plastics in the water, which is very difficult to see when you just look at RGB color. And unfortunately, all the wavelengths they have a lot of features in on land, in the water absorbs them. So radar, thermal infrared, SWIR, all of the longer wavelengths of light get absorbed. So we're using this technology to also kind of quantify the degree of human pollution in a lot of these environments, in addition to mapping kind of corals and different seafloor structures. And the data sets are big. So this is from our Guam campaign. This is the first entire reef 3D map at the centimeter scale over an area of tens of square kilometers. And so this video will show you kind of that entire environment down to a depth of around 70 feet on the forereef there. And it'll zoom in to show you an area of what the resolution looks like for this sensor. So there's a little patch here you can see, and I'll just skip ahead so you can zoom in to see what the full resolution is like for that patch. So that's the resolution of the sensor if you run it at full over the whole reef. Now you see lots and lots of coral structures, all of these hidden things that, you know, sometimes people have gone and dived. There's a little fishing line here. That's that line across the
Oh yeah, you can see that right there.
and we got two of them.
A couple
So
of them.
those ones we actually put in as targets to see from the aircraft, and then we took them out afterward, but we use it to measure and validate the airborne product. And then
So
map it.
Ved, the other ecosystems that are in serious trouble, like have declined by half, are the seagrass meadows and the kelp forests. And this seems to me to be really critically important, again, to not only measure what currently remains of the once flourishing systems, but to monitor them. There are efforts to try to replant both in places. And just as looking at the trash that's accumulating in coral reefs, oh my goodness, we just need to get greater resolution and the ability to assess change over time, which is exactly what you're doing.
And it's
Yeah.
such a lot to be done. You're really working with some of the local people in the communities as well, right now, to
Enlisting them.
enlisting their help.
Yeah, and actually I'll skip ahead to that bit because that's the most fun bit. And I can come back. But yeah, I
Oh.
sort of shift the way we do our field work. A lot of the Western nations do these parachute field campaigns where they go to a place, they do their work, they take the stuff, they leave.
Yeah.
What we have found is people are a lot more invested if they're part of the production process. And
100%.
so in Guam, we actually got a large NASA grant to train 25 pilots. This is through my collaborator, Professor Romina King, who's an amazing advocate for the oceans, particularly in Micronesia and Guam. But these are pilots now that are fully trained on these advanced aircraft. They fly them routinely. In fact, two of the pilots here have flown one of the reefs every 2 weeks for the last year and a half. So we have a time series of every change on that reef at 2 week intervals, which might be a bit excessive, but we wanted to just push it to the limit and see how much can you see, because this was an area with tons of tourism activity, and a lot of the impacts to the reef were just, you know, humans doing silly things on the reef. But this is giving them data about where to, you know, enforce management and how to change management practices, maybe provide people some training. We repeated this kind of capacity building in other countries as well. So I just did a mission in Madagascar last year. That community is heavily engaged. They're going through a famine that's caused by climate change. So all the people that are hungry from the central part of the country are moving to the coast to eat fish, but now the stock have collapsed. And
Yeah.
so a lot of their fish recovery relies on a healthy reef, and they're really paying attention to how to create a resilient reef so that the fish can come back, they can survive, the fish are happy, and the reef is healthy. So we've been trying to scale up this capacity building effort globally, and NASA has invested a ton in US territories and areas, but we're hoping National Geographic looks like they will be supporting a large global effort to expand this to 6 new countries. And then they get that, you know, the money goes straight to the pilots there. They get paid to map corals. They're invested in the data product. They use the data product. And then they, of course, have these drones so that they can answer questions that are relevant to them in their environments. And that's been really rewarding to see, but also just, you know, from a practical standpoint, you map more ocean, you get more done, right? When you are working with folks that live there, that care about it. So yeah,
It's exactly the model of the Hope Spots, and the model for the, you know, the HONU submersible program is to really do that community capacity building and make, really have them engaged. And I think that as we see, the creation of jobs that are tied to technology and to things that are not extractive, it really does help in the recovery effort of the reefs.
Right. Expeditions that have a lasting impact.
Yes.
And that's one other piece of that puzzle we have is this. Well, it's now become a video game, but it started off as just an AI called NemoNet that, of course, Sylvia is in. But this is a massively online citizen science video game where all these users in these different countries and anybody can pick up an iPhone, an Android device, or a desktop computer and start mapping coral that they have surveyed or we have mapped for them, and then use that data. We can use it to classify corals globally. So this reached millions and millions of people, and we still have hundreds of thousands of users. But in the game, you're introduced to different coral types. You learn about how to classify them accurately, and so you have to pass a few tests. But then once you start gaining confidence or regain confidence in your ability to classify, you start getting new data, you're training it for us. That data goes back to our NASA clusters of computers, and then they can classify that entire reef at a really high accuracy. So the countries that are mapping a lot of these corals are also playing the game and getting their local folks interested in their reef environment. And the side effect that we did not anticipate, because we were just interested in mapping corals and how to protect them. But there are many people that are in these reefs or islands that have never gone out and swum over a coral. Some of them don't swim, right? Or they're just culturally, that knowledge was lost. And they're now getting a new interest and getting to see their backyard for the first time and are super engaged with what they get to understand is just, beyond their doorstep. And then similarly, people in landlocked countries play this and have a great time because they never get to go and, see corals, but they're interested, they want to participate. It's sort of that effect you get with national parks, right? It's very easy to sell a national park because you can walk in it, but it's very hard to do that with a coral reef that's maybe 50, 100 miles out at sea, right? You need to have some sort of immersive experience. And we found that at least, this virtual way of exploring it has been very effective at bringing people a sense of what is there and how it is changing and why they should care. So we try to make the game fun and introduce different levels while also maintaining the scientific accuracy. So all these different players that contribute data, they're compared against one another. But what's amazing is they're doing a phenomenally accurate job of mapping the coral for us. And we don't take their inputs as truth. We end up doing a bunch of checks and comparing it to others and then running it through our AI to do a model. But the result is that we can now accurately map coral in these sites at an accuracy that's finally approaching what would be needed if I was a physicist to publish, which is 95% confidence level. Previously, most coral reef studies, sometimes the accuracy hovers at 50%, which I like to remind people is a coin toss. It's a guess. It's not a scientific result. In physics, the gold standard is 5 sigma significance, 1 part in a million. In coral reef ecology and ocean biology, the bar seems to be set lower, but that to me is not really acceptable when your life depends on that system, right? Your life doesn't depend on the neutrino decay rate that much that you might know of, but that's been proven to 5 sigma significance, right? But it has, ocean health, and half the oxygen that comes from it has a manifestly important impact on humans. So I've been trying to push this in the field that, it's not significant to get an accuracy that's really low. I mean, this is more science slide, so I can skip this. But one key takeaway from this plot is that when you use NemoNet and 3-dimensional data to classify coral reefs, it outperforms 2-dimensional data that does not have fluid lensing by a large factor. And that's not entirely surprising. These are environments that are very 3-dimensional. And so to study them and answer questions about them, you kind of have to think like a parrotfish in 3D, not in 2D where we just look down at a structure. So we're seeing good accuracy on the products. And as a result, we can go from a picture that's very distorted of a reef to a clear fluid lensing picture. that information is fed out to a video game that's massively classified and trained by gamers. And then that data trains an AI, and we can then predict for that reef where there's coral, what the percent cover of that coral is, and even what types of coral are present. So here you can see percent cover with about a 5% error rate. So this is the first, 195% confidence interval. And then here we're looking at coral morphology, the breakdown between branching corals and mounding corals with about a 9% error. And we can do that across really large scales, like entire, reefs in Guam. And then we're expanding this to other locations. So that's what I'll stop here because the rest is not yet published. But
Awesome.
Saving the ocean should be fun,
It should be.
and it
it
is.
should be. I mean, it's fun for all the players that play the game. It's less fun for my team that has to manage the server. But
Yeah, I can imagine that. It's just like, so much data.
No, but the before and after storms is another really important role for being able to map accurately the state of the reefs. I mean, you know that coral reefs and seagrass meadows and kelp forests, all the coastal, the living shorelines really are so important economically as well as intrinsically. But to be able to measure it, to be able to show before and after, to show the resilience or the lack of it, it's another whole dimension to how what you're doing, Ved, really is a change making in
that's very kind. I feel like we're still at the very beginning, but I'm hoping we can advance the technology much, much further. And this summer, actually, I'm very lucky to get this more inventor fellowship and have an agency kind of take a chance on me to develop the successor technology to fluid lensing and MIDAR, which is why I call the Holy Grail. That's full ocean depth imaging from an aircraft or space.
be able to see the ocean, to think like the ocean, to think like the creatures who live in the sea. That alone, just shifting the perspective, asking the questions, what does a parrotfish see? What does a deep sea fish? What's the world like from their perspective?
Yeah.
And then to bring ourselves into that world, see through their senses. And there's so much more. It's sound, it's light, it's the chemoreception is next.
Yeah.
Or all together.
Tell us a little bit.
The more I dive into this, the more interesting the story gets. So, I first thought the deep ocean is dark, right? And then I realized there's, apart from the bioluminescence, there's another source of light, which particle physicists had struggled with for a long time because they were trying to use the ocean as a neutrino detector and build sensors on the very bottom and then have these cosmic rays that hit the upper atmosphere scatter light and interact with water to detect these very difficult particles. But they kept this other, one of their detectors was picking up lots of bioluminescent squid and different things talking to each other, causing their sensors to go crazy. But then the second part is that there are radioactive calcium ions throughout the ocean that cause it to glow using Cherenkov radiation. So the same blue glow you get around nuclear reactor fuel rods is actually present in all parts of the ocean at a background level that's actually enough to cause, a detector to hit light. So that then changed my perspective. Oh, well, the ocean's not entirely dark. There's actually ongoing light emission at every cubic centimeter of seawater. So now I'm trying to go back to the drawing board with kind of the third technology and think, can we think of something that can see full ocean depth, right? We know of a few things that do go through a lot of matter, but they're very hard to detect, like neutrinos. Gravity waves travel through all matter, but they're very hard to detect unless you're a black hole merging with another black hole, which is, not something you really want near Earth. But we have, at least astronomers have for the first time detected, black hole mergers. So yeah, I'm starting way from first principles again and thinking, how do we how do we do this? And life has figured out acoustics, right? They use sonar echolocation to do this pretty well. Some animals use light, but I think there's something else waiting to be tapped into. And that's my new life goal is to try to get full ocean depth from space without having to get totally in the water. That would be
Oh, but you
my
still want to get totally in the water. I mean, you still have to take you in a submersible, you know.
yeah,
So
or submersible. That would, yeah, that's cheating, but I would love to do that. That would be another way to get closer to it. But
we'll get
But right, having the vision to take technology that can detect water on the moons of Jupiter and explore remotely as well as physically the distant places in space. We are so far behind getting to know this planet.
and I think that there's an urgency to me, not just for our sake of survival, but by and large, it looks like to first order, if you were to approximate life on Earth, right, it's aquatic. So the search for extraterrestrial life is sort of a misnomer, right? It should really be the search for extra oceanic life, because all organisms and life as we know it on Earth started in likely a deep sea hydrothermal vent. That's where a lot of the data are pointing to right now. And it looks like that's, life should be a strong signal. And right now, much to the chagrin of my Mars colleagues who say, oh, we should look in this dusty thing, I said, look, life should come up to you and try to bite you or poop on you or somehow metabolize you. And that's true of the ocean, right? If you put something anywhere in the ocean, something starts growing on it within a couple days, or something poops on you or tries to
yeah,
eat you.
yeah,
It tries to eat me every time I go in the sea. So that, to me, that should be what life is. It should be a very strong signal, unambiguous. And I think we have we've hit the celestial jackpot in that we have now 4 ocean moons we know of in our solar system, Enceladus, Europa, Titan, that have liquid water oceans, salty oceans, or hydrocarbon seas under an ice crust. And to me, that is like #1 target for life beyond Earth is these extra oceanic environments. But to explore them, you need the same technologies you need on Earth to explore life in the ocean. And we're just starting to get to those basic building blocks. And I'm hoping I can get more people that were in fields that I was in over into oceanography, just like Sylvia convinced me, because I think it's the final frontier, really, right? If you can crack that egg, you will likely find life faster than if you were to explore dusty, rusty planets, which might have, fossilized life on it.
yeah.
Or you could go to a sea on one of these other ocean moons and hope something comes up to you and tries to sting you or bite you or something. That is a
Or something. Yeah.
strong life signal, right? And I
I
think
just
it's
say
cool
something
to.
did I just hear you say something like the ocean is the final frontier?
I am a Trekkie. I've got a Starship Enterprise back here. Let's see.
Oh, there he I'm not even him jump up. Very good.
I think, they're not mutually exclusive, right? And I've wanted to be an astronaut for a long time, and I've also wanted to explore the sea, and it's space, right? There's
Exactly.
space without water, which is less interesting than space with water, is what I have learned.
Yeah.
So we will see. I will probably fail in trying to come up with a third technology, but we'll make some incremental progress, and then maybe one of my students will come up with the Holy Grail, or their students will come up with it. But if we could do that, if we could see the entirety of what's in the ocean from orbit, it changes our perspective entirely, and it allows us to also hold everyone to account, because right now we don't know what's happening on the seafloor in many places, especially in the high seas, right? And that's
Yeah.
something, you could do with underwater robots, and that's the other solution, is you deploy fleets of these things that map the seafloor and do it over time. But that's, for land, been the gold standard for how you conserve it, how you monitor it, how you hold people to account, right? They can claim to have X, hectares of Amazon rainforest protected, but if you can see it being deforested from space, you can't really, claim that that's true.
Yeah. Yeah.
So we need that same ability for the sea. And I'm gonna put everything I can in the lifetime I have to try to do that. But I'm hoping others will get inspired to pick up
Well,
the
it's the key. It's the key of, having both the curiosity and the, not fearing failure, because so many times science is so hard. You just feel like you're beating your head against the wall to get things done, but it's that tenacity and persistence that really counts. And you've proven that over and over again through all your efforts and work to date. So keep going. Please.
It's already be here. I will say the first decade of fluid lending development, the first 5 years I was told this will never work, except by my advisor who's very supportive. But everyone
Yeah.
just said this is gonna not work. And now somewhere with 10 years later, you're now like the de facto, this is the highest resolution thing. Everyone's like, yeah, that's obvious. We all, obviously it would work. And you're like,
Of course it
well,
would.
that wasn't always the case, right? But that seems to be the theme of science.
Yeah.
So now that I've learned that lesson and I'm going and trying to do the third invention, I find myself, worrying a little less about what others think. The only people you should really worry about are mathematicians and physicists who will tell you these are, cold hard rules. And then, you need new physics or new ideas to kind of get around them. But we will see. I'm
Yeah.
hopeful.
We're going to jump over to a couple of questions. Aline is asking, why are we investing so much money trying to find life in other planets and not protecting the whole universe that it's our ocean ecosystem? We depend on our ocean's life to survive, yet most humans keep fishing all of the life and destroying it. Cheers from Brazil.
Yeah, so I mean, when I grew up in Southern California by the ocean, and I loved astronomy, I loved space, and I loved the ocean. They were not that different to me. They're both really big, they're both really unexplored, they're both very difficult to live in and on your body, right? That excited me about them. I will be honest, at the time growing up, I kind of had to pick a lane. It was like I could go down the physics and astronomy and fundamental laws of the universe lane, or I could go down the cool ocean exploration lane. I kind of wish I did the ocean one earlier, but if I had done that, I would not have gotten the background in theoretical physics and mathematics that I needed to develop tools that we use in space to study the sea. So I feel like, yeah, I could have spent more time trying to protect things at the sea, but now that I came in with a space exploration background, I'm viewing the problems like a physicist or an aeronautical engineer would. And I think that has, at least in my one example, allowed a number of new technologies that have had a pretty big impact so far in revealing what we see there and protecting areas and managing fisheries for the first time using space exploration tools. So I don't know, it's that, sometimes if you see a problem and you run to it and you try to do something about it, you do it without having the proper information. So it's like you put out a fire, but that fire may have been set for someone preventing a larger forest fire, right? It might have been a controlled burn. To me, that's kind of the problem with some things that I see in oceanography, is that we are running into doing something without necessarily taking a step back and saying, what is the big picture here? How do we develop a tool that is not a one-off for this island or this community, but is a global system that can measure a global problem? Because it is not limited to one sea, one reef, one area, right? You need to be able to study this organism from space. That is the scale of this thing. And if we have a very narrow view, we run the risk of having narrow interventions that don't have a global impact. And one thing that my training in space science has taught me is, if you're going to study something of this scale, think like you do in space, right? Have this perspective you get from astronomy, where you think about really long-term things. Because as terrible as it is right now on Earth, and I don't want to be too grim, astrophysics tells us a lot of things about how lucky and rare life is. Our sun will go red giant in around 1.3 billion years. We'll run out of converting hydrogen to helium, and it will grow to be the size of Mars orbit. Entire Earth will be absorbed and swallowed. All life on Earth will be extinguished. So we have 1.34 billion years to get it right and learn how we understand these species and then transport them elsewhere or save the best of our planet. It's a long time. but it's a perspective you gain, I think, outside the field, that maybe helps you solve the problem you were trying to solve in the beginning, but with a global perspective. So I hope that answers the question.
A universal perspective.
Big thinking leading to deep thinking, leading to deep thinking.
So Patricia is asking, is there any possibility of developing a similar equivalent technology for murky water in the near future?
So yeah, mine are actually one of the other reasons I didn't touch on was ultraviolet and blue light penetrate murkier waters better than visible light. So definitely that's been one of our, I mean, I spent 10 years of my life in the Bay Area where you have very murky southern.
yeah.
So a lot of my tests were, can this work in really murky waters? And the answer is fluid lensing can even passively work pretty well. I did a large mission in Australia with it in Shark Bay looking at stromatolites as an early life form.
Stromatolites.
But yeah, I mean, there is a physical limit to how much turbidity you can withstand. And that's why I'm looking at trying to come up with other things that transmit well through water that penetrate these different optical constituents in CDOM and suspended sediment. But yeah, sometimes it's too murky.
Yeah, nothing's getting through. Benita is asking how she can participate in the coral reef mapping game.
Oh, yeah. So I think Gigi dropped a link in the chat. It's called nemonet.info. That website has a link to download all the apps for free. You'll see me and Sylvia in the video game encouraging you to play and giving you different insights as you play. But yes, please download it. We need lots more data for Tumon and Guam in particular because we're trying to push a big product for them out. And yeah, enjoy.
All right, we're going to get through our 3 more questions. John is asking, do you work just with the university or with any corporations? And also, he first saw Sylvia on the Fred Rogers show. I remember that. That was a great episode. 2 visits, yeah. And how do we
Keys?
Yeah, how do we get more schools to follow this work?
Yeah, so I mean, one of the reasons I moved from NASA into academia was to teach, to kind of pass on more of the stuff to the next generation. Ironically, I'm doing more NASA work now than I think I was doing when I was at NASA as a civil servant. But I work right now primarily funded by still NASA and agencies that we write proposals to. That includes 3-letter agencies, 4-letter agencies, philanthropic organizations. National Geographic has been a huge amplifier of what we do and storyteller. And then across education, I just put out a new textbook for physics for high schoolers that's going to 18 million high school students across the country. And there's a whole section on using physics to explore the ocean like you would space, and applying, kind of getting them hooked young, because the Apollo era, all that interest just happened because someone had pushed it, had suggested it, right? And we just need that same level of interest and excitement about what I think is the coolest environment I've ever seen. So it's growing. In terms of, what was the second question? Was academic reach, or?
I think Gigi dismissed that one already, but yeah, I was just asking if it kind of goes into the next question from Steve, that he mentions your next step is imaging the deep oceans from space, and hopefully the next generation will pick up on all you've done and take it further. What do you foresee the next frontier would be?
So I'm excited about some of the big advances in astrophysics that are being made with sensing, particularly with gravity waves. Gravity waves are a prediction from Einstein's general theory of relativity. I have a little picture of Einstein here on my wall.
There he is.
Riding a bicycle. Let's see if I turn this off. There he is. Speed
There he
limit E, right? So we've used measuring the strength of gravity on satellites. There's a NASA project called GRACE, which actually uses a laser interferometer between 2 satellites to measure locally how much gravity there is as these satellites orbit Earth. What they've been able to do is actually measure, in the case of California, how much water California's agriculture pumped out of the aquifer, because there's a gravity deficit over California from that action. that is the sensitivity of that instrument. You can, over the Himalayas, see slightly more gravity because there's more mass in that area. If you refine that measurement, you can actually measure a lot more detail about gravity perturbations around Earth. That's one thing that excites me a lot about trying to apply it to sea surface topography and seafloor topography. The second is gravity waves themselves. These are, right now, everything that accelerates in an inertial frame will produce these gravity waves. Black holes orbiting each other and merging will shed a lot of gravitational radiation in the form of gravity waves. Those are really big events that transmit very far, but they are stopped by nothing. Nothing. Light gets stopped by a mirror. It can be pretty easy, but gravity waves travel through space-time itself, right? These are objects that do not refract the same way that light does around different objects. And so for me, that suggests you could think much, much further down the technological ladder and say, can we use something like this to probe the interior of our planet, to probe the ocean, to probe what's in the column of water? And I think that that's not in the next 100 years out of the realm of possibility. It's a difficult measurement to make. There are other things that we can look at that transmit very far through water. High energy particles transmit very far. Some of them are naturally occurring in the universe. So, cosmic rays come from the sun. They also come from lots of active sources we have in our celestial backyard, but you can use that as a light to see the seafloor using some of these fundamental particles. And that's what particle physicists try to do when they go put a sensor on the bottom of the seafloor. They're trying to measure these particles that come from, a black hole, maybe 100,000 light years away, and they're trying to make that detection on the seafloor. So those are really long-term, the kind of things I'm considering is what can we do to see through water? And is there more than just light that we're thinking of? And if so, what? And how do we do it? So,
All right, we're going to squeeze in one last question, even though it is the top of the hour. Clark is asking, to the extent you can project, what is the timeline for making widely available and affordable the imaging technology that we've been profiling today?
Oh, that's a good question. So there are 2 NASA patents, so you, the taxpayer, own them. And we are trying to commercialize one of them, and with like a $1 research license for researchers that can then use the technology to map their area. Right now, everything that's NASA-funded research is free and publicly available. It's just a question of deploying these advanced drones to do the mapping and the sites. So my team has been doing a lot of capacity building. Those institutions don't pay for that. We try to fund it, but working with your local government and legislators to ensure that the respective agencies have the funding they need to make sure those technologies are matured and are translated into commercial products is a great start. I think fluid lensing you'll see pretty soon in the coming years available, widely. But some of the other more advanced ones take time to develop, and
Sure.
I'm not particularly driven by profit in research, so it's all about the science return, no matter the cost. But I remind people, Congress was persuaded to fund the James Webb Space Telescope at a cost of $14 billion to the taxpayer, and it looks away from where everybody lives. So imagine if we could just make 1/10 of that investment looking down where everybody lives and depends. I think it's a pretty easy case.
Yeah. Well, before we close today, Sylvia and I would like to say thank you. Thank you, Ved. Thank you so much for joining us today. And thank you, our producers at Ocean Elders. And mostly, thank you, Dive In community, for diving in with us all these episodes over all this time. And we're really, really grateful for everyone that shows up and participates in these conversations. Water connects us all. We are going to be back soon. And until then, remain curious and tenacious, just like Ved, and take care of the ocean.
As if your life depends on it, because
It
it
does.
does.
Thanks again, everyone. We'll see you next time. Thank you, Ved.
You're both so much. Live long and prosper.
Yes, please do.